Okay, so today we'll look at locks in OpenMP and also talk about some advanced task handling. So let's start with critical sections. So we already discussed critical sections, right? So this is an example that we had looked at some time back. So what is this doing? Essentially it's running a loop over an array, and in this loop it's trying to compute the sum of the elements as well as the product of the elements, right? So sum and product are initialized to 1. So this is partial sum and partial product, right? So we discussed that if we have multiple threads and I want to divide the work amongst these threads, then instead of updating the same shared variable, what I should do is I should keep a partial sum and a partial product, right? A variable which is local, which is private, and once I have computed my part of the computation of the elements, whatever operation needs to be done, at the end I go and update the shared variable, right? So I hope everybody remembers this. So now in this code it doesn't matter so much, but there's one issue over here, right? What is that? At the end, each thread is going to enter this critical section and update sum, right, with the partial sum that it has. And then it's going to go down and enter this critical section and update the product with the partial product that it has, right? Now suppose that thread number 0 finishes first, it comes here, it updates sum, and then it goes ahead and it starts updating the product. It enters this critical section. And at this point in time, another thread, let's say thread 1, comes here and wants to update the sum, but it won't be able to enter the critical section. What does critical section say? Critical section says that only one thread is allowed to enter a critical section at any point in time. Okay. But these two operations are completely unrelated, right? So if another thread was updating sum, it wouldn't matter to me, right? Because I am updating product and another thread is updating sum, so I don't care. It's not going to cause any race conditions, right? What I want is that two threads should not simultaneously be updating sum, or two threads should not be simultaneously updating prod. But it's fine if one thread is updating sum and one thread is updating prod. I don't want to, serialize that. So critical section does not do that for you, right? So there is an extension to critical sections in OpenMP, and what you can do is you can give names to critical sections. Okay, so you can say #pragma OMP critical and you can specify a name, section 1, right? And over here I say section 2. So then it knows that these are two different critical sections. So what it will ensure is that no two threads enter the critical section 1 together and no two threads enter critical section 2 together. But at the same time, you can have one thread in critical section 1 and one thread in critical section 2. Okay, and this is a small example to illustrate that. Whenever we enter a critical section and whenever we exit the critical section, we've just printed it out, right? And over here you can see some thread has entered critical section 1 over here, and then it got out of critical section 1, right? And then some thread entered critical section 2, and over here some other thread entered critical section 1. So at this point in time, there are two threads, one in critical section 2, one in critical section 1. Okay, so that is now possible. So if I have two critical sections, I can give them names, right? If I have 10 critical sections, I can give them names. What if I have critical sections which are dependent on the number of elements or the size of the data that I have? Right, then I cannot give them static names. I cannot say, critical section 1, critical section 2 and so on. I can't give them static names. I don't know how many elements there will be at runtime, right? Maybe I'm taking some input from the user. What do I do in that case? So in that case, I need to resort to locks. There are other advantages of locks also, but this is one differentiating thing from critical sections, right? So what are locks? Okay, so we're going to look at a simple example of histogram updation. What is happening over here? So there is an input and the size of this input is 2 to the power 26, and there is a histogram which has 2 to the power 20 elements. I mean, just think of it as that you have a huge document and you're trying to count the occurrence of words, right? So you're trying to count how many A's appear, how many the's appear, how many times the word study appears and so on, right? So think of this histogram as the words and input size as the document, right? So there's a huge document and you want to count the occurrence of every word, right? How many times it appears in the document, okay? So in this case, we are going to simplify it. Instead of having an actual document and words, we are going to assume that these are all integers, right? So the input consists of 2 to the power 26 integers, and the histogram that I want to build is of size 2 to the power 20, right? So everybody understands what's a histogram, right? Just counting the number of occurrences. How do we do this? So this is a simple program to do this. So I start by initializing the INP, the histogram, to all zeros, right? So I haven't written that piece of code. And finally, I time this section where I actually go and do the updates. And what are the updates that I'm doing? I say hash pragma OMP parallel. So this is the parallel region. And so I'm parallelizing this for loop. And key is a private variable, right? Everything else by default is shared. And if you remember, if I have a hash pragma OMP for, right, the variable of the for loop is automatically made private by OpenMP, right? OpenMP takes care of that. Obviously, it can't be shared. Okay, so key is private, I is private, and everything else is shared. So now what do? I just run through this entire input and I look at every element, I extract the key and I go and update or increment that particular histogram entry. So that's the code for histogram updation. So what is the issue here? Do you see any issues? If two different threads read the same integer in the input, they may be at different locations, but if that value is same, then they will have the same value of key, right? And then they'll go and try to update the same histogram entry together, and that will cause a race condition, right? So if I run this program, so when I run it with a single thread, then this is the output I get. So I'm also printing, at the end of the day, I go and add up all the entries. The sum should be 2 to the power 20. In this case, the sum is correct. And the time it takes is 2.93 seconds with one thread, right? And when I run with 4 threads, it takes some time. I don't care what the time is because my sum is incorrect. And why is it incorrect? We've already discussed that, right? There's a race condition because these threads are trying to update the same entry. Even though there are only 4 threads, right? But you can see that how many times the race condition has occurred, right? Quite a few times. So what's the fix for that? This is one fix that we've already seen, right? Put the update in the critical section. Can you do tricks like what we did earlier with partial product, partial sum? Can you do stuff like that here? So you can do that, but you have to replicate the entire histogram, right? So in some applications that may be feasible, in some applications that may not be feasible, but it's not scalable, right? Because as you increase the number of threads, you're taking up more and more memory, right? So it depends on how many threads you're using and the application. So in order to do that, you'll have to maintain a separate copy of the histogram. Each thread will have to maintain a separate copy of the histogram, and in the end, you'll have to merge all of them, right? So that is going to have its own overheads. So you have to be careful that, you know, whether you're going to get benefit out of it or not. You have to take a lot of things into account. Okay, so let's ignore that solution for the time being, and let's look at this, right? So this is one solution. I put critical here. Can I make use of the naming of critical sections that we just looked at? Okay. Yeah, how do I use it if I want to use it? So you can't use variables. You have to give a name. It is something that the compiler recognizes, right? That this is critical section 1, critical section 2. So key is a variable. It's determined at runtime. So you can't say critical bracket key. It can only be a static name, right? Okay, so it's not easy to use named critical sections over here. So let's see what happens with critical. So when I run this program with critical, the sequential code took 2.93 seconds, and with 4 threads with critical, it takes 21.6153 seconds. Right? Critical has overheads. Using critical sections is expensive. Here we are just doing a very, very minor operation inside the critical region, right? We are just doing one addition, which is fine. If I had a substantial code and the critical region was small, that would have been okay. But here my entire code is so small, right? All I'm doing is I'm assigning something to key, which hardly takes any time, and then I'm getting into a critical region to update the histogram. So most of the time in every loop is going to be taken entering the critical region, exiting the critical region by OpenMP to ensure that only one thread is executing this part, to implement that critical region code. So this doesn't work. We've seen the problems with critical before also, right? That's where we had shifted to that partial sum, partial product and all that. So we know that there's a problem with critical. So what do I do? So the solution to that is locks. How do we use locks? Locks are variables. So they are implemented using variables. So you can declare an OMP lock T structure. Okay, like here. What are we doing here? We are allocating 2 to the power 20 locks. As many as the number of histogram elements, as the size of the histogram. Right? How do I use locks? So first I have to initialize the locks. I have to initialize every lock before using it. Okay, so here I am initializing the locks. So for that we basically use the OMP init lock function and you pass the address of the lock. Right, so I have to use a for loop and initialize all the locks. And how do I use the lock? When I want the lock, I call the OMP setLock function and I pass to it the address of the lock. It must be initialized, right? And how do I release a lock? I call OMP unsetLock. Okay, same arguments. So what does a lock ensure? So what will happen if one thread gets the lock and then another thread tries to get that lock? It's going to wait until that lock is not released by the first thread. So it's a blocking call. What's a blocking call? It means that it will not return until it does not get the lock. This performs pretty much the same function as what we saw with that critical section with the name, right? Critical section section 1, critical section section 2, right? So except that we are passing a particular lock. So for every histogram entry, I have a different lock. This lock is indexed by the key. So now I have one lock for every histogram entry, right? That's what I wanted, which I couldn't do using critical sections. Once I'm done with the lock, I have to call OMP destroy lock to release the lock. So again, for any particular lock, it can only be acquired by one thread at a time. So if we run this code, this is what I see. So definitely I've got rid of the overheads of critical. So with critical it was taking about 21 seconds, but at least I have it down to like 3.4 seconds with 4 threads. And if I increase the number of threads to 64, I start seeing some gains. Right? With 4 threads, I'm still not seeing gains. It's still worse than running a single thread. So why is that happening? Lock unlock has its overheads, right? The point here is that different threads are able to get their respective locks simultaneously. Critical section was not allowing different threads to enter that region of the code. Right, here different threads, if they are working on different elements, at least they can enter the code, right? So you get some advantage out of that. That was the whole point of using locks here instead of a critical section. But the degradation is because locks also have overheads, right? We have got gains. Eventually with 64 threads, I've got better than what I had with a single thread, but it's not satisfactory. I've got like factor 6 speed up, but for that I had to use 64 threads. What we would like is linear speed up, right? That's the ideal scenario. Another issue with these locks is that they take a lot of memory. How many locks are we having? We are having as many locks as the number of histogram entries. There's another side effect of that. I'm accessing the histogram. The histogram is very large. I don't expect it to be in the cache, right? It can't fit in the cache. So that's not something I can take care of. I mean, I'm accessing entries at random, right? So how can I ensure that they'll be in the cache? But the locks is something that I maybe could have kept in the cache. But in this case I can't, because the number of locks is also 2 to the power 20, which is huge. So because the number of locks is huge, they are also going to get swapped out of the cache regularly. So I can't hope to benefit by the cache with the locks. Currently what have I done? So this is my histogram. these are the entries of the histogram. I associated a lock with the first entry, a lock with the second entry, a lock with the third entry, and so on, right? I have a lock with each and every entry. But an alternative that I could have done is I could have just taken a block of entries and associated a lock with that. What's the trade-off? The number of locks is reduced drastically, right? Depends on the number of entries I have in the bucket. So I'm calling this a bucket, right? Depending on the number of entries in the bucket, the number of locks reduces, right? So I have lesser memory, and if it is small enough, then it might even fit in the cache. Look, the histogram doesn't fit in the cache, but the locks may fit in the cache. So what is the advantage? The advantage is that my memory footprint has gone down. Maybe I can make use of the cache out of that. And what is the disadvantage? So if two threads are trying to update histogram entries which are in the same bucket, then they are going to again contend for the same lock, right? And that's going to slow down the code, right? Reduce parallelism. So we run this code with 4 threads and 64 threads, and this is the kind of pattern we see, right? So let's just observe a few things over here. So when the number of buckets is very small, right, there are just 2 buckets, then with 4 threads it's taking 18.7 seconds. Why is that? Because there's a lot of contention, right? There are only 2 buckets. Most of the time these threads are wanting the same lock. And as I increase the number of buckets, this is coming down, and that is expected. As I increase the number of buckets, there will be less and less contention. Okay, the same behavior is observed with 64 threads. It starts with a large number and then it comes down, right? This is also as expected. But let's have a look at when the number of buckets is 16, right? Then what is the time taken by 4 threads? About 8 seconds. And what is the time taken by 64 threads? 102 seconds. Why? Because there are more threads which are contending for the same buckets, right? 64 threads with just 16 locks, they are going to contend, right? Whereas when you have 4 threads and 16 locks, that contention is less. When you see for 256 buckets, so this gap is becoming closer, and when you look at 1024 buckets, then 64 threads has already started to do better. Now because the number of buckets is so large that even 64 threads are able to work in parallel. So the amount of parallelism that we are getting with 64 threads is substantial. And eventually when you reach this large number here, 64 threads is doing considerably better than 4 threads. So this is just to give you an idea about how contention scales with increasing number of threads. So we see that with 64 threads with large enough number of buckets, we do have good performance, 0.5 seconds. But again, as I said, right, it's not linear speed up. With 64 threads, if the sequential code is taking like 3 seconds, I was expecting much better, right, with the 64 threads. Definitely sub-second and maybe something like 0.2 seconds or something, right? So there is actually something called atomic in OpenMP. It's also called a mini critical section. And this is not like a critical section for the following piece of code. Instead, it's a critical section on the memory location. Okay, and there is only a fixed set of operations that you can do, right? It's like memory update operations, right? Increment, addition, and so on. Some limited set of operations that you can do. So it says that the following memory update in the next instruction will be performed atomically for this memory location. What that means is, if there is a thread 1 and a thread 2, right, and thread 1 comes to this instruction trying to update hist 1 plus plus, and thread 2 comes here and tries to update hist 2 plus plus. These are 2 different memory locations. So even though the code is the same, so that's where it differs from critical section. It's not a critical section on the code. It's on the memory location, right? So it says that it will allow both of these to happen in parallel. But if let's say thread 2 was somewhere else, maybe not in this piece of code, but somewhere else, maybe I called a function somewhere, and inside that function a thread 2, was trying to do hist 1 minus minus, right? And this was inside hash pragma OMP atomic. So if thread 2 is executing this code and thread 1 is executing this code, and both of them are trying to update hist 1, it will not allow them to happen together. This is ensuring that that particular memory location is not updated by two threads at the same time. That's what it does. Okay. So you can read up the OpenMP manual on what all is supported under hash pragma OMP atomic.
So in the function, doesn't it the hist 1 will be some other variable which address will be different?
That doesn't matter. The memory location is what matters. The address. It just figures out that whether the address being updated is the same or not. That's what matters. This is runtime support.
If we have one variable in the main and one variable in the function,
right?
So with the same name, but treated as a different, they both have a different address. No, like there is a function, it also have a, and in the main we have a variable a. So this, the address of this a will be different from that one.
Yeah.
So in that case, if we are doing this atomic operation, so it won't, both A's are having different addresses, so in that case it won't be a matter that
yeah, so both of them can happen in parallel. It's the address of the variable being updated. What is the variable? Hist of 1. This is hist of 1, the first entry of the histogram, right? The address of the hist 1 is the same. So look, at the end of the day, it doesn't matter who's doing what operation. What matters is that at the time this load is issued, it's going to be a set of instructions, load, store, or some kind of an atomic instruction being executed. There's going to be an address that is going to be passed to it, right? 0x something something, which is stored in some register, right? All that matters is what is that address. If there is another hash pragma OMP atomic already happening with that address, it's not going to allow this to happen until that does not complete. Right? So this requires support in the hardware to implement. This is runtime. This is not static.
Even if you use different variable names pointing to the same location, it will still.
Yeah, absolutely. So we run this code and you see some very good results. With 4 threads, I'm almost seeing a factor 4 speed up, right? Just a little bit less than factor 4. And with 64 threads, it's not linear but close to it, right? Substantially good. Critical sections and locks have considerable overheads. That way, atomic is very, very light. But the drawback of atomic is obviously that it only applies to the following memory update instruction. That's all it applies on, right? But most of the time that does the job for us. Typically, we are doing some very simple operations, right? So this is something you should keep in mind.
can atomic be multi-line? No.
No. Atomic is only for a memory location, and that memory location is identified by the update in the next instruction. Address of the update in the next instruction. So it's only a single instruction. So there's a limited set of operations that you can do with atomic. So you can find that in the OpenMP programmer's guide.